Hello again, and welcome to another review session for your final exam in Calculus 3208, brought to you by CDLI. Today we're looking at the first installment in our section or unit on the calculus of trigonometry, and as natural as things can get, we're going to look at limits first. So we're going to talk about some basic trig limits. Alrighty. So today we're going to talk about sort of two fundamental limits involving trigonometry, and those are kind of the things around all of our other trig limits are based on, really. And then we're going to talk about evaluating some simple trig limits based on that, and in our next session we'll look at some more complicated ones. Okay, let's get rolling. So the first of our two fundamental limits that we need to figure out here is this guy, sine of x divided by x. So this limit right here. So how do we figure that out? Well, if we don't know what it is, and we don't really have an algebraic technique for it, you know that a couple of things that we did way back when we were first looking at limits is we can look at a numerical depiction of what's happening as x gets close to 0, or we can also look at it graphically. So if we look at this numerically first, we're going to see what happens as x approaches values of 0 from the right, and you can see I just took a screenshot from my graphing calculator here, where I got it to do all the numerical business for me. And on the second table here, it's the same idea, but I'm looking at it as x approaches 0 from the left. So as we get really close to 0 from the right, what happens is we can see that the y values are all approaching +1, and it looks like the same thing is happening here from the left. So if we had to guess based on that, it looks like this limit is going to be equal to 1. We could look at directly at a graph of this function, but one that sometimes gives folks a little better understanding of why this limit actually equals 1. Over here, what I've done is I've given you a graph over on this side. And in blue, we have y equals sine x. And in red, we have a graph just of y equals x. And so those are basically the numerator and the denominator of our expression. And what you can see is that the closer we get to 0, as we move from the left and the right, both ways in towards 0, what happens is those two functions look more and more alike. The sine function flattens out and has a slope of 1 right at 0. So what we can see is that since those two functions get infinitely closer together as we get close to 0, it only makes sense that one divided by the other should be equal to 1, because they're pretty much the same thing. So that's a bit of, both of those things are just sort of conceptual understandings. Neither one of them gives you a proof of this limit, of course, but hopefully that gives you an idea of why the limit as x approaches 0 of sine of x over x equals 1. Alrighty, let's move along. Okay, so the second really important or fundamental limit that we look at with trigonometry is this one, the limit as x approaches 0 of 1 minus cosine of x divided by x. All right, so to evaluate this one, we do actually take an algebraic technique, because now we have that sine of x over x business in our back pocket, so we can use that to help us out here. So you might notice that on the numerator of this particular limit, we have a binomial. And when we have a binomial, and we check to see if we get an indeterminate form. So on the top, this gives us 0 as it does on the bottom. So 0 over 0 is indeterminate. Then what we do is we're going to use our technique that we used way back when of multiplying the numerator and the denominator by the conjugate of that numerator. Okay, so up top I can see what happens is 1 minus cosine times 1 plus cosine gives me 1 minus cosine squared. And on the bottom, I'm just going to leave it in factored form. And the reason I want to get 1 minus cosine squared up top there is we should all remember that 1 minus cosine squared is equal to sine squared. That's one of our Pythagorean identities from Math 3200, if that's where you learned it. And once we've got that, then what we're going to do is we're going to think of this sine squared that we have right here as being just sine of x times sine of x, instead of just sine squared. And we do that so that we can sort of separate this limit into two fractions that are multiplied together. So I've got this fraction, which looks awfully familiar now, and this fraction. So I split up my numerators and my denominators to say it's just two fractions that are multiplied together, and that's perfectly algebraically legal to do. Then we're going to employ a limit law, which says that if I have a limit of a product, that is the product of the limits. So the product of the limits here is going to be the limit as x approaches 0 of sine of x over x, and the limit as x approaches 0 of sine x over 1 plus cosine x. So let's see, this guy on the left, we've already figured out that this limit is equal to 1. And over here on the right, if I try direct substitution now, sine of 0 is equal to 0, And cosine of 0 equals 1, so on the denominator I have 1 plus 1, so I end up with 1 times 0, and that gives me a value of 0. So this limit actually turns out to have a value of 0. One little note before we move away from this. We we set this up in the first place as 1 minus cosine over x, but just as easily we could have done it this way, as cosine of x minus 1 over x. Why are they going to have the same value? Why are they both equal to 0? Well, it's because cosine of x minus 1 is, of course, think about this for a second, cosine of x minus 1 is just the negative of 1 minus cosine x. And limit laws tell me that I can take the negative and put it out in front of my limit, just like a constant multiple. And so I know that this part of the limit right here is all equal to 0, and negative 0 is still just 0. So either way we look at it, that limit is equal to 0. It doesn't matter what order the terms of my numerator are, so the limit of the conjugates, both of them over x, is actually equal to 0. Okay, let's take a look at something else now. This is what we call what I call the trig limit toolbox. So what we're going to do is we're going to keep those two fundamental limits in mind. The limit as x approaches 0 of sine of x over x equals 1, and whichever way we call that last one, that limit turns out to be equal to 0. We're also going to keep these two things in our back pocket as well. They're very simple. They're just evaluated by using direct substitution. We know that sine of 0 is 0, and that's fine, and we know that cosine of 0 is 1, so that one's also okay. But these four things help us to evaluate pretty much any limit that we can come across that involves trigonometry. Those things, along with all of our other limit techniques that we already have from our previous unit on evaluating limits. Okay, now having said that, there's four of them there, but there's really one of those four things that's the most important because it shows up the most often, and it's this guy right here. Sine of x over x, the limit of that as x approaches 0 equals 1. We will see that I'm just ballparking it about 90% of the time. So watch out, that one comes up all the time. Okay, let's get down to some examples now. So here's one that says the limit as alpha approaches 0 of sine of 5 alpha over alpha. All right. Well, this is kind of similar to what we know. Our limit that we have that looks like this, if it was in terms of alpha, is the limit as alpha approaches 0 of sine of alpha over alpha. That would be equal to 1, right? We don't quite have that here, though, because of this 5. Okay. One of the basic ideas that we try to run with for these trig limits is that when I have the limit as anything at all, so you can call it junk, what do you want to call it? Limit of stuff. So right here, we're just going to call this stuff. So the limit as stuff approaches 0 of sine of stuff over stuff, that's equal to 1. So in this case, we call it alpha here. Before we call it x, you can call it theta, you can call it stuff, you can call it spaghetti and meatballs. It doesn't matter. But if I have the limit as stuff approaches 0 of the sine of stuff over stuff, that limit equals 1. So what I have in this particular limit that we're trying to evaluate now is this 5. Well, if I want to make this work, I have to have the same thing in these three positions. It has to be the same stuff everywhere. Now, trying to take sine of 5 alpha and split that apart so that I just end up with an alpha up there, that's possible, but it's not easy to do. We know we have some compound angle identities and double angle identities and stuff we could use to attack that, but it's much easier if we just try and get this one and this one to be 5 alpha instead. Okay, I can't just randomly throw a 5 in right here because that changes the value of my fraction. So what I can do, the technique is to take this and multiply it by 5 divided by 5. So if we do that now, I have the limit as alpha approaches 0 of 5 times sine of 5 alpha divided by alpha. Okay. Now this, divided by 5 alpha. I had to multiply both the top and the bottom by 5. Now, one of the limit laws that we should remember is that the limit of a multiple, a constant multiple of a function, what we're allowed to do with that is take that constant multiple and pop it outside in front of the limit. So I can rewrite this as 5 times the limit as alpha approaches 0 of sine of 5 alpha divided by 5 alpha. Now we're close, except for this bit. Well, that bit is actually quite minor. What we do with that is there's lots of techniques to deal with this in terms of a substitution, but it's probably, I think, the easiest way to deal with that just to say that if alpha approaches 0, what's 5 times alpha going to do? You guessed it, it's also going to 0. So I'm allowed to actually change the variable that I have on my limit there to say the limit as 5 alpha approaches 0 of sine of 5 alpha all over 5. So 5's a bounder everywhere. But this bit right here now, we recognize that as the limit of stuff as stuff approaches 0 of 5 stuff divided by sine of 5 stuff divided by 5 stuff. Whatever. These 3 things are all the same. And if those 3 things are all the same, then that limit equals 1. So the actual overall limit here is just 5. Okay? So there's a quick way to tackle that slight variation on what we started with. Another example. Okay, this one looks a little bit trickier, but if you keep your dancing shoes on here, it's not so bad. The fact that I have this 7 in the denominator, that's what makes it a little bit different, but there's actually not much to this at all. All I'm going to do with that is I'm going to remember that this is the same as the limit as theta approaches 0 of sine of 6 theta over theta multiplied by 1/7. And then I can take this 1/7 because it's a constant multiple and get rid of that as well. So this is 1 over 7 times the limit. And now I'm going to try and set this up for myself in the long run here. I know that if theta approaches 0, so does 6 theta. So I'm going to put that in there now and get it over with. So 6 theta goes to 0 of sine of 6 theta over theta. And if you remember our technique, what we did here was we multiplied by 6 over 6. So if we multiply by 6 over 6, we have 1/7 of the limit as 6 theta goes to 0 of 6 sine theta, 6 theta, sorry, all over 6 theta. Okay, so all that stuff there, I know I've got another constant multiple that I can throw out in front of me. So that's going to give us 6/7 of the limit as 6 theta approaches 0. And my numerator here is going to be the sine of 6 theta divided by 6 theta. And we've got the limit as junk approaches 0 of the sine of junk over junk. So this is 6 over 7 times 1. And we get a limit of 6 over 7. Okay? So not much to that one either. Lots of fun. Let's try a different one now. Okay, this looks like it's got a little more fun to it. So we have the limit as theta approaches 0 of sine of theta over cosine theta minus 1. Now, what we do here is we should recognize that sine theta divided by cosine theta minus 1. Both of these things, my numerator and my denominator, look a lot like some other limits that I had. So we're going to remember that this is the limit as theta approaches 0. If I had this, sine theta over theta, I know that is 1. And I know that if I had the limit as theta approaches 0 of cosine theta minus 1 over theta, I know that that one actually turns out to be equal to 0. All right, so let's tackle this then. What I want to do is if I could get this numerator to be sine theta over theta, and if I could get this denominator to be cosine theta minus 1 over theta, I'd be in business. And since this is a fraction, it's perfectly a-okay for me to multiply the numerator and the denominator by the same thing, which is 1 over theta and 1 over theta. All right, so this gives us the limit as theta approaches 0 of sine theta over theta divided by the limit as, sorry, we'll leave it all as one limit for now, cosine theta minus 1 over theta. Okay, so let's tackle this then. That's going to be equal to the limit as theta approaches 0 of sine theta over theta divided by the limit, now this is a limit law, the limit of a quotient is the quotient of the limits. So we have the limit as theta approaches 0 of cosine theta minus 1 over theta. All right, now if I try to evaluate this, look what happens. I get 1 on the top and I get 0 on the bottom. So you might think that means I'm out of luck and I can't finish this, But 1 is a constant, and a constant over 0 is actually not an indeterminate form. This limit is out of luck. So the only answer we can have here is that the limit does not exist. Okay? So there's a fun one. Alrighty, let's move along. This is the your turn question, and it says the limit as x approaches 0 of tan x over x. So the hardest thing about some of these problems is just kind of, well, how do I get started with this? So if you want a tip for how you get started with this one, I'll give you a little hint here. And the little hint I'm going to tell you is try to use your quotient identity first. That tan x equals sine x over cosine x. Try that and then go at it with some algebra, and I think you might have some success. And don't be afraid to split limits up into more than one limit. All right, I'll jump to the solution. So here's the solution for this one. And as you can see, making tan x into sine x over cos x really helps out, because then we get this, and this, and this, and you end up with a value of 1. Nice limit. Okay, let's highlight some of the key ideas that we saw here. So some of the key ideas that we saw here were to evaluate any trig limit. We manipulated algebraically to try to find the limit in terms of one or more of these monsters. And they're the same ones that we highlighted a few minutes ago. Sine x over x equals 1, cosine x minus 1 over x as x approaches 0 is equal to 0, and then these two are the real simple ones. Just substitute and solve. So it's important to keep in mind that all of the limit laws and techniques that we learned and that were developed in the second unit of this course, they still apply. So if you need to get all that in your head before we get into the really difficult ones in the next section, I'm going to recommend that you do this. Okay? Hope that was helpful, and we'll see you next time.